so shall we start? Okay. So this talk will be only loosely related to MySQL. I do a lot of benchmarking, and I often ask the question, how do I make the graphs? So this talk will be about how to make that graph in 17 easy steps. So that's an output of Sysbench comparing multiple storage devices, both in the read-only and read-write cases. And why visualization is important, I have some examples here. And the terminal is smaller. So the raw data of this looks like that. So it's a lot of Sysbench output. We can look at one. So it has the seconds granularity data. So it's consisted of 60 time series data. So if I would like to graph that, it's 60 graph. 60 graph is, too much to show in a 15-minute talk. So we have to do something, which can visualize this better. And we will use R and Gpplot2 for that. So in order to use the stuff I'm going to use here, we have to pre-process the data to put that into our data frames. For that, the data needs to be in this format. The first column is second. You can see from the R code that from the column names, what does it actually mean. So this means that for the first second of the benchmark on this storage device, or it was a read-only test with this many threads, the metric is Sysbench transactions per second, and the value is more than 2,000, right? So here, in a more realistic scenario, you have lots of data for each second. You will have MP-stat data parsed for each second. You will have VM-stat data. You will have probably all the MySQL admin variables. So you can choose from the R code, you can choose what is interesting. But for the sake of this example, I created a parser for this. So it's like I usually have a script which takes the raw benchmark, which I run in the raw benchmark output directory, and it just parses the data and outputs it like that, and redirect it to a file. And that file, I read from R, and do the graphs from that. So how to read the file from R? We are creating the data frame with the read.table, which will read a table from a file. This is the file which is the output of the given script. So it's 1 line per second per metric. We name the columns, and for each graph, we do a subset. For example, here in the Sysbench TPS data frame, we are subsetting the Sysbench OLTP data frame. The metric will be TPS, threads will be 256, the read-write case, this storage device. We convert the value to numbers. In these examples, if you download this isn't necessary, but as soon as you have MySQL admin output there, for example, which has some non-number metrics, what you will see is as soon as you make the graph, each metric will appear in the y-axis as a text, and you will see a gray smudge or something like that near the y-axis with a graph that doesn't make sense. This function here, it only creates some aggregates. I usually like to do that. So this is also R has a nice IDE called RStudio. This is the first graph I'm going to show you soon, but here is the aggregate data frame. It's not too visible, I guess, but it calculates for the given benchmark. Each of these benchmarks are an hour long. It calculates the standard deviation of throughput, mean throughput, the 95th percentile, and the maximum. So for each case, we have kind of a tabular data as well. Okay, so initial graph, the R code for that is this. The R code will grow during the presentation. So we take just the 256 thread read-write benchmarks at first. And in order to create a graph with Gpplot2, you have to create a graph object with the Gplot function, and you have to add at least aesthetics and at least a geometry. Here at the aesthetics, I tell that the x-axis is the time, the y-axis is the value of the metric, which is the TPS now, and I plot it as lines. So you saw that example, you load it into RStudio, and it will look like this. You can change the geometry. For example, one I like is geom text, which will just output the values as text. Okay, I don't have a label. I will show geom text later, I guess. But we can change it to geom jitter, which is a jitter plot. So the issue with this plot, with the line plots, is that the individual values are always joined. So in this black area, we have absolutely no idea what is happening. And it's a quite high variance, right? It matters if it's 6,000 or 6.5. So we can do jitter plots. But still with the jitter, with plotting only the dots, we still have some dark black areas. So we can use the alpha channel feature of the jitter plot. So we are plotting transparent dots. So where the color, which in this case is black, is more vibrant, we have more samples in that area because the dots are plotted on each other. Where they are more light, we have only one sample. Next thing is this seems to be inconsistent at the first time, but it's only inconsistent because R auto-detected the axis. So you can use the expand limits function to set the start of the y-axis to 0, which will yield to this graph. And you can specify a geometry and a color, where we specified that it will be the storage column from the data frame. It doesn't matter what do you specify as color. If something is a different text or a different number, it will be assigned a different color, and that's it. And this automatically generates the legend. The legend is not that nice to be here, right? So we add to so these are always additions. So from here, the R code would be too much to show. So I only show the additions. So we can put the legend here like that. And I like this because it shows the flexibility. This legend is quite ugly because we are using alpha channel for the dots. We actually figured this out with Fred at last FOSDEM. So the color in the legend is really light. So we can override the legend to have the alpha channel of 1. So we have the regular color dot here. We can add the label to the y-axis. We can add the label to the x-axis. This is fairly common thing. We can use more vibrant colors like that. And in the legend, it was still a bit ugly because the background was gray. So we can set it to white. So it will be quite seamless. So this is still a single benchmark run. So this is one time series. This is 1 hour worth of sysbench. In the next example, what we change is the x-axis. Instead of putting the time there, we are extending the data frame. So we are not restricted to a single thread configuration, but we are examining all the threads. And in the x-axis, we are putting factor threads, which will result in an output like this. The first column here practically will be the single threaded, second is 2 threads, 4 threads, 8 threads, etc., etc. So this kind of graphing is, I think, a good way to see how something scales and where is the optimal degree of concurrency. If you specify the x-axis like that, there will actually be a hidden x-axis for each column which is time. So it is still in it's still ordered by time. Okay, the other feature I like in R is faceting, because with faceting you can make easy comparisons. Here, in this example, I added all runs for this storage device, and I'm faceting based on based on the read-only, read-write column. So here I will have two graphs. First is the read-only, second is the read-write. And they will have matching scales. So it's like automagically if you're using faceting. So it's pretty easy to compare them, right? Read-write value is slightly lower, but that's because the read-write test in sysbench. So it's different because in the sysbench transaction, if you're doing read-only tests, there are some statements that are simply not run, which would write the database in the read-write case. More faceting, so you can do multi-column faceting. Here so the first argument of this is the vertical. Dot means that I don't facet vertically, and this is the horizontal. Here we are faceting in a way that we are using the read-only, read-write, and the storage device. So in the first row we will have the read-only data. In the second row we will have the read-write data. So for all the three storage devices, the read-only and the read-write performance is comparable. And why this type of visualization is important, we could say that it could do some transactions per second, or it could have this amount of response time. But benchmarks with a single number as a result are not telling you too much, right? It's important how consistent is that performance is. And from the jitter plot, you can see that, for example, in the read-write case, that after 256 threads, it goes more inconsistent, while not only it will be slower, it will be more inconsistent as well. And here in the read-write case, we have some spikes up, actually. So that you see that it's not that vibrant, and most of the samples are in the lower region, but some of them are in the upper region. Okay, so we have some stuff to set the graph title, which will appear here, and the only thing which remains ugly in this is the caption in the threads, because we did so much faceting. Then these numbers are kind of pressed together, and now they are unreadable. We can fix that by setting the properties of the x-axis. So we are writing them with 45 degree. In order to save the plot, you need to use the ggsave function. So by default, while you are working with RStudio, it has. So let's go to the last example. And this graph will actually take some time to generate. So see, it started to generate it because it's so many dots. Because it has, for each row in the data frame, it has to plot a dot there. So it takes some time. And there it is. So if you like it, during the period while you are working with this, you see an output here. And you can save this with the ggsave function at the end of it, if you like the graph. Okay, all the R code on one slide. So actually, to generate that graph, the R code is this. It was just step by step. This goes to my GitHub repo, where all the examples are there, and all the sample data as well. The sample data is from a recent benchmark, and the customer was kind enough that I I could use it in this talk. And that's it. Thanks. Are there questions? Yeah?
I think I've got it now, but I was a little bit confused by step 12. We had a factor, which is your threads. So the notion of factor is different from factoring, is it, or?
The notion of factor?
With the factor here, which is your threads, and there's a hidden thing around pi, which is to do with the width of each thread.
So factor just means discrete values. So let's try to remove factor here and just graph the threads. And the issue what we will see here is that it will be linear, right? So this is 1, 2, 3, 4, 1000. So the factor means that I'm supplying discrete values to you, and each discrete value should have its own, an equal area on the graph. That's what factor does. So without factor, it looks like this.
That's something different from faceting. That's slightly different from faceting.
Yeah, faceting is multiple graphs next to each other with the scales matching.